So let's start with our afternoon session of the conference. And it's my great pleasure and honor to introduce our first speaker of this afternoon session, Professor Joseph Seade, known as Seade, Professor Seade. And he is from Mexico, Universidad Nacional Autónoma de Mexico. And he will talk today about Chern classes and uses of vector fields on singular varieties. So please, the word is yours.
Thank you very much. For first, we actually thank very much. I should thank the organizers. I should thank the organizers. I'm very grateful to be here. We have Ernesto, Miriam, all the teams of people, and I thank you for being here after lunch, thank you. And well, I'm not really talking. This is not that kind of colloquial type talk. So at some stage it will be elementary. I hope not boring. And it's a subject that which I've been working for decades since my PhD a few decades ago. And well, I will start out from the bottom, try to get somewhere. So what is the title? Let me start from the very scratch, very quickly. We've been talking already about in classes, in several of the lectures. Let me say a few words just to settle my point of view, to motivate you. Then the aim will be moving to Chern classes for singular varieties. But let me start from scratch. So let me start with the motivation, which is we have a vector bundle that means a triple, total space, base space, and a projection. Where let's assume a simplicity that means that the move manifolds and everything in operation can be modular. And then the basic question is how can you develop this and how to do it? Develop this trigger by definition if it is isomorphic to x times the fiber. So how trigger this? And let me precise it. The exercise below makes it precise. If K is the fiber dimension of the bond, B over R over C, then if E admits a subordinate E prime of dimension R less or equal to K, which is trivial, if and only if it admits R sections which are linearly independent over K at all points. Okay. So how trivial about this? Let's see. A few examples that you will now very examples of this. If we start with a group, then we can look at traceability of the three arguments, which is the tangent space of identity. And then using the group multiplication, we translate that basis all around, we spread it all around the group. We get as many vectors here in the vector fields of the dimension of the group. So we can go to this tree. Very easy example. Another family of examples comes very important. We start with two manifolds, and we take a function which is locally, which is generic transformation. We take a regular point, we look at the inverse image. That's a submanifold of complementary dimension, and which naturally comes with realization of the normal bundle. Yesterday we heard about how the portrait construction, but this is the very starting point of the portrait construction. Okay, so things are not always achieved. For example, we know that if we take an in-dimensional sphere, it doesn't admit a single vector field of singularities. If you doesn't admit even one-dimensional figures of bond. Okay, so we have a picture that we all know. Here we have a sphere, and a vector field with two singularities, a vector field with one singularity of index 2. No way to construct the vector field without singularity of the sphere. Okay. So in general, we about how to tell if it admits a section with no singularity. That's well understood. But more generally, you know how many sections does it admit which are linearly independent everywhere over R, over C, or even holomorphical if you are in the holomorphic category. Okay, this is a question that can be difficult and rather solved. Let me give an example. Let's start with a complex, two-dimensional complex surface with an isolated singularity. Okay? How to construct that? That can be, for example, the zero set of a map from C3 to C having a critical point. For example. That case for this question is also easy, but more generally you can consider, for example, a holomorphic line bundle over a Riemann surface, a compact Riemann surface. Take S here as the zero section, and assume the volume is such that the self-introspection of S in E is negative, which is equivalent to saying that the Chern class this volume is negative. Okay? Then in that case, if you get S embedded in a image of the zero section, you have E, you have the zero section, and the conditioning I impose on the negative self-intersection tells that you can blow down this analytically and get a complex surface singularity with an isolated normal singularity. Okay, so take one example of a surface with an isolated singularity. Now remove the singular point, so we look at it, it's a complex two-dimensional manifold. And you look at this tangent bundle, it's a holomorphic bundle. But you can forget all the complex, everything, and just think of it as being a really vector bundle. Then it's an exercise, not trivial, but it's an exercise to show that this bundle is always trivial as a real vector bundle. The reason it is just because the intersection is a three-dimensional, the smallest sphere of singularity, which are three manifolds, oriented three manifolds. The tangent bundle for every three manifold is bigger, and then the normal bundle, coordination one for everything being oriented is also bigger. Okay, so it's very easy. This bundle is always trivial as a three vector bundle. So now if we think it is a complex vector bundle, we'll see disregard the holomorphic structure. Just the fibers are complex vector space. Then you can ask if this is sort of trivial as a complex vector bundle. And you can tell that sometimes yes, sometimes no. Yes. That happens if anonymity singularity is called, which is what is called numerical recurrence. All coordinate singularities are numerically constant that we do to a complete intersection at a particular object. So, for example, coming back to this case, if this is the Riemann sphere, and we take a bundle with Chern class less than -2, what you get is never numerical curve. Okay? So here there are sometimes yes, sometimes no. So now we remember that it's actually a holomorphic bundle. And we can ask if this is trivial holomorphic bundle. And then a famous statistical conjecture tells you that look, this is never the case unless you actually don't have a singularity, unless one is there. That's an open conjecture. Yes, I know to be true when this is a complete intersection. No, when this is the hypersurface. In many cases, no. For the problem, no. Okay, but in general, it's an open conjecture. Okay, so this very different triviality can be rather solved. Now, let me move forward. Now, let me come to giving a definition of Chern classes, most of you know, we will get quickly. Consider, for a start, a real. Yeah, thank you. Let's start with a new orientable vector bundle, the real manifold. And then we ask if we can construct a section of this bundle. Okay. Then, assuming that the fiber dimension is less or equal to the dimension of base for simplicity, It's an exercise to show that even over given a calculation of certain composition of the dates, you can always build a section of the skeleton for dimension. Sorry, for dimension k one. And not built because the file is highly correct. The period cohort of the period. Okay, then look at this element. So the structure is set at two sections. One becomes the skeleton for this dimension. Your structure is extended with no singularities. On the next dimension is like the dimension beyond the class of the volume, it's a cohomology class here, which is independent of the variable changes. In particular, that means that the other class is the primary obstruction for constructing a regressive section. If the dimension of the variable is the dimension of the base, this is the only obstruction. And in the particular case where the volume is the tangible volume, this is just the classical fortaleza here. Okay? Now, what if we want to construct not one section, but two linear independent sections? Or three, or four. How to measure? Well, it's not having the same process, classical process from 70 years ago, using a direct topology. And from now on, for simplicity, that we consider complex vector model, not holomorphic, complex. Just for simplicity. Okay, then in our case, the hardware is CK, and then assume that this is 2K, so the real dimension of the wire is less or equal to the dimension of the base. Then again, for every R less or equal to K, then the node by WRK, because following is simple manifold of complex of the normal R frames in CK. So before we use the fact that the fiber, we want a no-zero section of a vector space, so the fiber was somehow the sphere and the spheres are highly connected. Now, the fibers we have in question are these different manifolds. And again, we know elementary well-known topology that they are highly connected. And the first non-zero group is isomorphic in integers in this direction. Okay. So again, using this elementary topology, we can see that given these conditions, we can construct for every R, we can construct an R frame or R linear independent sections over C, over this another frame, and we can always construct here the limit. Given a calculation of the base, we can always, for every R from 1 to K, there always exists an R frame over the skeleton of the corresponding dimension. Okay. And then, whenever we have to go to the next step, for each phase of the next dimension, we make an obstruction at one point. That obstruction is an element in the corresponding local homotopy group, which is in that direction is exactly as the model of the integers. So for each phase of this dimension, we have a lot of obstruction in the integers. This gives you a cohomology class, which by definition is the corresponding Chern class. Okay. So Chern classes are the primary obstructions for constructing linear independent frames. That's in all dimension. There is one Chern class in which direction from 1 up to K, the final dimension. And we have contained the top Chern class, which is the sum of all this, that element in the cohomology group. This is somehow it's very different, but in the spirit of the Chern character that we saw yesterday. It's a different thing. It's somehow it's an element in the cohomology group, defined by the Chern classes. This is a unit, so it has an inverse, that's an important factor to use later. And notice that when the base is a closed manifold oriented, we have compared one. And then cohomology classes can be mapped into homology. And we can think of Chern classes as being cohomology classes. Okay? And in that case, they have a very geometric nice interpretation. The top one, which becomes the lowest degree by quality, is You take a generic section of the model and you look at the zero set. That gives a homology class, which is the dual of the Chern class. The next one, you take two generic sections, and you look at the point where they become linearly independent, and so on. Now, there are many other interpretations. Generally, for example, they are regarded as operators in the control ring, and they can be polar varieties. They can be defined in many ways. They can be defined axiomatically. There are many properties. And they are extremely powerful and important variables in geometry. We've already seen them appearing in several of the lectures in this meeting. And this has nothing to do with the rest of that, which is a beautiful jewel. It's just as a toy, as an example of the power. Let us prove this very important theory. That we all know. But before the dimensional sphere does not admit an almost complete structure. It seems to have nothing to do with the topic of this lecture. Okay. Let's just take just as a toy example. Let's see. Suppose then it has three classes C1 and C2. In H2, homology and in H4. Okay. Then we can form this polynomial C1 squared plus C2. Evaluated on the rotation cycle and divided by 12. This polynomial is what we call the second top polynomial. This number is what is called the top genus of our four-dimensional almost complex manifold. A powerful theorem fixed homogeneous growth for complex surfaces extended by a feasible for almost complex manifolds tells you that this is the index of the D-bar operator, versatility. So we are reducing an atomic problem. The big theory tells me that then, if this is an almost complex structure, this number divided by 12 is an integer. This one is in H2. H2 is pure dimension. So what you're saying is that this number is a multiple of 12. But this number is the other characteristic, which is 2. So if we explore a mixed and complex structure, we find that 2 is a multiple of 12. Not possible. Okay? Of course, one could say, and what about the 6? That would be something because that's another problem. And for creating a simple mix, tell you that the corresponding number is essentially C1 times C2 divided by something. And both classes are 0, so you're saying that 0 is the multiple of an integer of the block. Okay? But in this case, it goes so that gives you just a little taste of the power of changes. Now let's move forward. Now we move to singular varieties. Here are a couple of examples in some drawings. And then the singularities appear precisely where there is no tangent moment. So when you speak about, if you want to speak about index of a vector field, what does it make sense it make? To start, what sense it makes to speak about tangent vector field when there is no tangent moment? But let me not go into that. So for a start, I will consider varieties in some invariant space, and the varieties will have isolated singularities. So I just take a continuous vector field invariant space with an isolated singularity, and such that restricted to the variety it is tangent. So implicitly, we are talking about something I will define later, or what is called stratified vector fields. Okay. So you have your analytic space, and a vector field tangent to this new fact to start. What sense, what should be the equivalent of the Kokharikov index? Okay, let's an example. Take a homogeneous polynomial. Okay, then being homogeneous, all straight lines are tangent you see those set because it's homogeneous. Then if you take the radial vector, it's automatically energy derived. What should it see? It's indexing. More generally, also you can also consider, for example, suppose that you have an even number of variables. That's one thing. Then you could also consider this that nothing the partial here of F you have to C2 minus C1. And you alternate by person. You can take any order, because by pairs is a change sign of one bit. Then all of these are all can be found in vector fields, because it's trivial to show that this any such vector field is tangent to the vector surface in question. And that will all the fibers of the function. What should they use in this? Of course, it depends on what we call the index. Okay. So this is the kind of question that we can start working on the 80s. And well, there's not a single definition, a single answer, but it depends very much on what properties of the index has. You can has many properties, which depends which one you want. And that brings you to what concept of index you want to define. And that is much related to asking, when you have a singular variety, there is no tangent space at the same variety. You can ask who plays the role of the tangent volume when you come to the singular. We'll come to that question later. So talking about indices, there are three, let me say, three main notions of that. Three main notions for me of the index of vector fields in singular varieties. One is known as GSV, another one is invariant, another one is analogous function. Let me say a few words about each. Before I just recall a few facts about singularity theory. We start with a holomorphic map. Just Chern, the only way we get what happened here, the critical one, which may or may not be isolated. Then, when you have a situation, by definition, you need to find it in the local non-critical level of the function. That means you look at the regular value, you look at the inverse image, and you look at the portion of the inverse image contained in that small ball. Okay? Of course, these all have to be made precise. What those small mean, what is it, and so on. You see, that's very easy. Well, just listen quickly. Here, first, given F, first it's a sufficient small sphere, which is called a minimal ball, a minimal sphere. That means that it meets essentially transversally the regular part. Something else. So a sufficiently small ball, it exists. And then once you fix the ball, you take a regular value, so it meets transversally the given sphere. You have to be a little more careful, but essentially means that. Okay, now it's told that by definition, this minimal fiber is a style manifold. So it has automatically homotopy type of a Seade double complex of new dimension. That's for free. But now, if F order has the function order has an isolated critical form, then you will prove in the famous book in the late 60s that it has a homotopy type of a wedge spheres of middle dimension. In the context here, this has complex dimension n, real dimension 12. And it has a homotopy type of a bouquet of the spheres of middle dimension. How many? A certain positive number. That number is called the middle number. Okay? And then if I just want to repeat this, let me say that this was improved by meaning of itself in all dimensions for 2, and then by later on to show in general it is not only homotopy type, but FP is diffeomorphic to a ball of the dimension 2, to which you attach handles of middle mode index, as many handles as the middle number. And this number can be completely generalized at the dimension. Okay. So we have what invariant, the minimum numbers are very important invariant to the right. Now, if the critical point at C of A is not isolated, then this is difficult to look at the type of a single context of implementation, but the topology is more complicated. In that case, it is known that it is diffeomorphic to a manifold, to a ball of the correct dimension, to which you attach successively handles of different dimensions, of different morphisms. Okay? The way, how many handles you have to attach at each stage is measured by a number, which are called the delay numbers. Okay, and those will be relevant later in the talk. So the delay numbers were introduced by David Massey, and they are by definition the multiplicities of something which are some analytic cycles, which are called delay cycles. And so to define these cycles, they arise from the theory of polar varieties, which was developed by Lay and Tessier. And if you have a function, you choose a good system, a generic good system of linear coordinates. Then you take the critical set of functions, which is where all the values for the special given vanishes. And then for each k, you look at the zero set where the last partial derivative vanish. And then you look at the points of non-universality. Okay. Well, you look at the points where things vanish, minus the physical point, the closure, and then you look at these analytic cycles. And those are the definition. The polar varieties. So these are the polar varieties. That's the polar variety. Okay, so the polar variety is you remove this critical set. You look at the points of the plane of a generic plane, the points of non-universality, and you look at the push. What's the polar variety? And then using that, you define the delay cycle, which is by definition for each k. The k delay cycle is you take this polar variety intersected with the vanishing of the next partial derivative, and you remove this polar variety. So this is it. These different analytic cycles, which are called the local delay cycles, is going to be used by David Massey. And then for the generic coordinates, this intersection is in a single point. And this intersection number by definition the corresponding delay number. And then delay numbers give you the topology of the local minimum factor. Okay. Now, this is the theorem. You know what I said? The delay numbers tell you the topology of the local minimum factor. Now let's come to these activities. So the first one I want to mention, I started studying the varieties. It seems not to be of any use at all until there is a started discussing with Alberto and Javier Van. Here we found some applications to actually to the theory of the working vector fields, and we define them in general. We started studying them in general, and it is known as the GS index, or what is known Seade and Markovsky. And the basic idea is very simple. Look at the hypersurface Chern. They are critical. You can look at the special fiber, see what you have to like it. You can think of it as being the degeneration of looking at the non-critical levels. And you see how non-critical levels degenerate as you go to the critical level. That's classically as a chart. Well, now you can think that at each stage in non-critical level, you have a vector field, y continuity, and this vector field has isolated singularities. And then, as the regular fiber, the generic fiber degenerates to the singular fiber, a number of series of the vector field collapse to the singularity. Okay. So we just don't know how we do it. You have the series of a generic fiber, as this tends to the special one, these singularities, collapse to the special point. You count them with the analytics, you count the property, and that's usually the definition. Of course, this can be made of precise. And well, you can define also as the review of a certain mark using the variant effect. You can define in a very similar way to the definition of the electrical properties as the review of a mark, with the idea of the and then you get this number, it turns out these numbers have some properties. The first is that if there is no critical point, this is not equal in usual case. If you have an isolated critical point, and the vector field is radial, scaling everywhere from a small neighborhood, then this index is this number, 1 plus minus 1 to the times the middle number. There is a middle number of two sides. So it means that this index is putting together in one concept the middle number and the comparative index. And it has, well, the definition extends easily to complete intersection theorems, and this opened a line of research on indices of vector fields. This was extended by one small, using chronological algebra in a very, very interesting way. If you have any dimension in any coordination, suppose that A is the dimension of B, there is a singularity, and it's embedded in some coordination, it doesn't matter anything. You can consider the K components of dimension A or B. And if you have a homomorphic vector field, you have a contraction. You go to N minus 1. You go top the A, and you could keep on with the different functions, and you put a zero. So this is the kind of constraint complex. If the vector field and zero have isolated singularity, this complex has finite dimensional homology. You can take the characteristic, that's a number, that's a well-defined number, that's called the chronological index of the vector field. That's defined for every isolated singularity in any dimension, complete intersection or not, whatever. But if this happens to be a complete intersection, this coincides with GS variance. Okay, so that's very interesting. On the other hand, not in the direction, you could consider compact manifolds, another subvariety with advertising levels, and then using differential gravity, chain base theory, Lehmann, Suarez, and so on, extended this definition to arbitrary index, the virtual index, and again, in case of isolated singularities, this coincides. So this is in general assuming they have a complete intersection. They do assume a complete intersection, and if it's inverted isolated, it coincides. And then just to mention, it was also extended by Edelin and Hussein Seade for one forms instead of vector fields. And that has the advantage that it makes sense in defining indices for collections of long forms. And the idea that morally the index that we will see, the index somehow corresponds to the top Chern class. Index of value vector field or a long form corresponds morally to the top Chern class. With this trick of collection, because we say graphical collections, they define similar invariants for all Chern models. And so on. Okay. Now there's another concept which is the variable index. You have the variable index, you can also define by variation class in the 65, for just for one particular class of vector data which is called normal variable. Then this was extended by King and Trondheim in 91, but the paper was not published from 20 years later. So in the meantime, not knowing about that paper, Alberto, Marcelo, and I worked on everything which is I was supposed to read about it, become the same index. And the idea is very simple. If you have, suppose you have a single variety, suppose for simplicity variety, you can put in a small link, the range of the topic, and then you have the vector field. And somehow you measure the difference. So this real index was measured since the lack of the reality. How far the electron field is from being zero. Okay. And that's essential for deploying of linear shorts, and it was an essential step for the construction of Chern classes. Finally, there's the local order structure. It's a very, very important invariant introduced from McPherson in 71. He used it only for one forms, which were of a specific type, called gradable forms. He visualized what is called the order of structure of an analytic state of each form. This was adopted by vector fields, or regular vector fields, and then extended by results in general. This is another index of vector fields. The idea is to use the natural walk, which means that if you have a singularity, you remove the singular set, and you replace it by all units of tangent spaces at the general line. Okay. Give it a space. This space comes naturally with a bundle, which is called the Nash bundle. And that Nash bundle, this projection is a bichromophysi away from the singular set within this image. And then the Nash bundle extends the tangent bundle to the singular line. Okay. Those are the different indices. And then just let me, I think I will skip this. Just let me mention that the difference between the Drainer index and the GSB index is independent of the choice vector field, and it is opposite the minimum number. Now let me move to Chern classes. And again, as before, there are several extensions of this concept depending on which properties you want. And as for me, this is much related to the question of who plays the tangent, the role of tangent bonding in the grade of tangent bonding. Okay. So one way is to stratify the space. That means just use the expenses of a partition where each stratum is a smooth manifold with classes are tangent bonding, and it's different strata are due to generalizing. And you take the union of the tangent moment to the structure, you can take the below the tangent moment, or you can take the natural with its natural, or for complete intersection with our natural moment, which is the virtual tangent moment. I will say more. Or you can take also the tangent or the cotangent sheets. Those are natural objects that we can play the role of tangent and there's a simple set. Let's discuss this briefly. First, it's stratification. You look at the stratification, you can look at stratified vector fields. And you can look at the try to construct stratified frames. You know that each vector field is tangent to the corresponding structure. And then technically it is very complicated, but the basic idea of variations follow the classical idea of proportion theory. Just everything is far more complicated. You know some good ideas, but the same principle of trying to look at our structure for constructing appropriate stratified vector fields yields to homology classes, which are called the short space. That was going to be middle 65. Now, those are very, very nice conceptually, but it was impossible to work with them in order to a few years later, there was the theory of Dennis Solomon about the simple witness classes for in the real case, and he outlined some ideas from the linear and lottery about the theory of Chern classes and singular varieties. And then later, by a different way, not following the ideas of Dennis, but first in his thesis, proved that there exists homology Chern classes that satisfy the properties outlined by between the idea of Dennis was known as with the linear model with conjecture, and that was proved by McPherson using exactly the order of function in our problem, and we get very, very good like this. And what he showed is that there's a, it has to say, this was easy what can part. The first is that there's given a single variety in a complex manifold, at the right, everything goes analytically. There's a unique covariant function from the category of complex and regular varieties to abelian groups, whose value on a variety is exactly a group of constructible functions, and it satisfies this normalization problem. And then the conjecture was that there exists a natural transformation from this function to homology that for manifolds assigns to the constant function 1 the concurrent dual of Chern class. Okay? So what my person is doing is that to every constructible function on an algebraic variety, he assigns a period of homology Chern class. Very, very fancy. And then a few years later, Seade and Marlene Schwartz proved that the Schwartz classes live here, the McPherson classes live here. Well, there's a value, and then they show that considering McPherson function for this constructible function, the short classes map to the McPherson class. Okay. So this coincide, and then we are now known as the Chern Schwartz McPherson class. So these are very important homology classes. And when trivial finding out in the zero for compact varieties, this class is just the only characteristic of the class. Okay. Now, one can also consider a little technique. Suppose that the variety is defined by a regular section. We have a holomorphic bundle of rank complex dimension of the fiber K over a manifold of dimension N. You take a regular section, and that gives rise to a complete intersection X in N. So in this setting, you can take the tangent bundle of N restricted to X. You can take E restricted to X, this makes the normal bundle, and you can take this, which is no longer a bundle but a virtual bundle, in element in K here. Okay, and this also somehow plays the role of the tangent bundle. And then you can take the Chern classes of this, which by definition is take the Chern class, the total Chern class of this, and you multiply by the inverse of the Chern class of this. That gives you total Chern class of this, and that gives you the Chern class, and you can be natural. This definition, as such, requires this to be a complete intersection. But that's just for simplicity. If you don't have the setting, these classes are defined in full generality. They were defined by putting in all generality using the same classes. Good. And you have this very canonical classes. So you have the football classes. And then one can show that both short classes and football classes, just as usual short classes are associated with the index. All these are associated to the corresponding indices that are identified. We have this theorem. In each dimension, the McPherson class is represented by an implicit cycle in this way, where these are a generalization of the regular index. So you take the synthesis of the correct dimension and you put them here, you put here a number, which is given by the regular index. And this is your cycle, which represents this class. And similarly, you take the same thing, but instead of putting just this number, if this is a complete intersection, sorry, a hypersurface, or hypersurfaces, instead of this number, you put this, or this is the local minimum fiber, and you take its only characteristic. then the debate is equal to that. And this is essentially, for what I said, very much related to the geophysics. So we see that a strong relation between the various indices and this various generalization of Chern classes. So summarizing, if we have a similar variety for manifold independent bonding from Karekov index of the Chern classes, in zebra set for completing planar section, we have a rich dependent bonding, various interpretations of indices which are equivalent somehow, and the fructose classes. Or you can look at the linear transformation status. I forgot to put here the radar index and the varieties Chern classes. Or you can look at the mesh bonding, the stability structure, and get the varieties classes. And then so you know that the 12 classes of the class conside. And we can show that we know that for indices, this difference of these two the minimum number. So it is natural to ask what is the difference between the footprint classes and the travel person classes. That same question arose at the same time in various settings by different people. Since the declaration in one point of view, the poor different point of view. And this gave rise to what is called. So in the simplest case, we have the following theory. If you have a complete intersection in a regularity which has only isolated singularities, then the zero degree footprint class differs from the zero degree travel person class by the sum of the different numbers. In general, when you have non-isolated singularities, you look at the difference of the footprint classes and the travel person, and you have one difference in each dimension from zero to that of the singular locus. Those differences are called minimum classes. So you have a minimum class in each dimension from zero to that of the singular set. Then these are kind of interesting variants because they are defined globally as the difference of two generalizations of Chern classes, but they are concentrated in the singular locus. What will this invariant measure? What will be the minimum class measure? And okay, just to give an answer, we could identify the local base cycles, usually the topology of the middle file locally. Well, it turns out that this concept can be globalized. If you have a projective variety, so from now I'm speaking about your work with Roberto Callejas del Regal and Michel Morgado. Roberto passed away 3 years ago. He was in Brazil, Michel is in Brazil. And we can define the global polar cycles in exactly the same way. We look at the concept local recycling in a hypertensity. We could look at the closure, and you can define some concepts that you need. Whenever you have a singular variety and a within specification, you can look at each one at a normal, a transversal, which is a normal slice, which is a transversal, intersected with a small ball, intersected with a singular variety, and you look at the under, you go to the normal slice. Then within this, you can take an intersection with a generic linear function. So this one is called the normal link, and this one is called the normal vacuum. That's the notation from varieties and mathematical person. Then there's this concept, which is was introduced by Chern, which is what we call the normal mode limits, which is the other characteristic of the transversal with weights in a constructible function. It's associated with every constructible function. You can have this normal index with respect to the constructible function, a number, and then you can define the global Schumann and divide the version of global McPherson classes. They did it in the affine case, that's why I'm saying it's essentially good to them, because they did it in the affine case. We need it in the projective case, so what we do need for our projective manifold, you take the code one dimension more, you take the definition, and multiply the rest. And then you have this, which McPherson cycles, the main cause because also missing, which is given by normal mode synthesis times the molar varieties. So you have this projective McPherson cycles, and you can define the global delay cycle, which are the same as the correction test. Why this name? Because one has the following. So the affine delay cycle is restricted to every point with the local delay cycles. So when you have a hypersurface, at each point you have the local delay cycles, and you can globalize them to have global delay cycles. So you can define them. And then our main theorem is that if you take a hypersurface, a projective hypersurface, you take the topological boundary and C1, then for each claim, the minimum class is determined by this K class of the topological boundary times the delay cycles. And conversely, the delay cycles are determined by this class. So in other words, you have a compact hypersurface. At each point, you have a local cycle that gives the topology of the local minimum pattern. You can globalize that to global cycles. On the other hand, you have the minimum classes, which are defined as the difference of different classes that generate the Chern classes. And it turns out that the information you get from one side is essentially the same as the information you get from the other side. Just as a corollary, if you look at minimum classes, it has quite intriguing. Suppose a singular set is of dimension D, and you look at the minimum classes top dimension. So, of lower dimension, as you can see in the well, it turns out that that is just taking the fundamental class represented by the singular set, and at each point of the regular part, you look at the conversor, you have a mathematical singularity there, that has a minimum number, you take that minimum number, you take this, so, and that's the minimum class. So in that case, the minimum class are some very beautiful geometric objects. What the definition in general, that's something which we did not understood. This is a subject which is very much in process and very much.